day, ladies and gentlemen, and welcome to the CUAHSI Cyberseminar conference call. My name is Jaquilla, and I will be your operator for today. At this time, all participants are in listen-only mode. We will conduct a question-and-answer session towards the end of this conference. If at any time during the call you require assistance, please press *0 and an operator will be glad to assist you. As a reminder, this conference is being recorded for replay purposes. I would now like to turn the call over to Mr. Richard Hooper, the President of CUAHSI. Please proceed, sir.
Thank you very much, Shaquilla. Hi, everybody. Thanks for coming. We have a few people still signing on and getting ready, but let's. I think we should get started. Today, I'd like to talk to you a little bit about observatories and particularly the CZOs in the context of what's been developed in CUAHSI's Hydrologic Information Systems program over the last few years. Now, the HIS project has been led by Dr. David Maidman at Texas, and there are a number of other PIs in the project, including Ilya Zazovsky at San Diego Supercomputing Center. We also have Mike Piasecki at Drexel, Dave Tarbot at Utah State, and there are others as well. Praveen Kumar has been involved in many others. So what I'm doing is going to be giving a brief presentation of some of their work, particularly in terms of how I think it could be assisting in the development of the CZOs. This is one of a series of seminars this fall. All the information is on the CUAHSI website. And Dave Tarbot in Utah State is the organizer this semester, so if you have ideas for additional seminars, particularly this spring, please feel free to contact Dave. And of course, let us know how this works for you in terms of technical problems and other issues. John Duncan is having a well-deserved day off today, so he's not on the call today, and I'm being the presenter as well as hosting it, so I will try to keep up with the chat box, but recognize I'm talking in, trying to see how everybody is doing. So bear with me as I do that. So let's get started with the seminar. It's a fairly brief seminar, I think, today, and I hope it will we'll have opportunities for a number of questions for you to ask. So let me get started in the kinds of efforts we've been going on in getting the CZOs going and talking about the broader observatory efforts, such as the major research equipment efforts, like the Waters Network that CUAHSI is working with the Cleaner Project Office of Environmental Engineering on. The kind of questions that we get when we present these concepts at NSF are this: what really is an observatory? And we have been struggling, as you all well know, for many years writing these various grand challenge questions. And what we're getting, the guidance we're getting now from Doug and others at NSF is we've got to start to focus those grand challenges down to what are really the decadal goals. This is all a matter of focusing towards getting much more designable science questions and a way that the senior management at NSF can try to evaluate the importance of the science we're proposing to do versus the investment we're asking them to make. So, for example, we've had grand challenges stated like predicting water quality and quantity anywhere in the United States. And that should get translated into saying, well, what stops us from doing that now? And so, for example, what we're lacking is a quantitative integrated model of groundwater and surface water and the need to describe flow paths and residence times predictions. We can keep on developing that to a point towards why particular technologies are important for us to deploy, why we need a certain scale of an observatory, and how the observatories work. There are other examples on the slide, such as what's the effect of low-frequency climate structure on hydrologic extremes. And the needs there run more towards land surface atmosphere interactions and a lack of a model to make those linkages across these systems with very different dynamics and to predict aspects like soil moisture. Or something like adaptation and scaling of river networks, vegetation, and landforms, which is going to require some kind of integration of fluvial geomorphology and ecohydrology. My point here is that as we develop CZOs, and one important part that CZOs are going to contribute, is trying to focus how this larger scale investment by the National Science Foundation will translate into exciting and innovative science. And in part, CZOs are really here to prove a concept that this kind of study, this kind of structure, can actually result in innovative science. The next question we often are asked is, as soon as you get past one level of the science questions, is, well, then how many of these things do you need? And the answer should arise organically out of the question. In other words, the network structure should be implied by those specific decadal goals. So an example, if we think about groundwater, surface water interaction, we can start thinking that we need observatories in different hydrogeologic settings and maybe with different depths of the unsaturated zone. The point of all of this is that the observatories should serve as models of other systems, and that we should have the ability of transferring information from these intensively studied observatories to less studied areas, so trying to emphasize the ability to make inferences. With all of these efforts, modeling is very central to everything we're talking about with observatories. And for that reason, I'd like to take a few minutes modeling in slightly more specific terms, and then move into how the work of the HIS project can assist with this. So let's start first by thinking about how we as hydrologists, as environmental engineers, as aquatic ecologists, et cetera, how do we approach modeling? How do we look at environmental modeling? If we start with a particular landscape, I think this is a stream in Montana from the crest of the continent, Hydrologic Observatory perspective. When each of us look at this setting, we see different things. For example, for hydrologists might look at this picture and note something about the wetted perimeter of the stream and ask questions about what the stream flow was, what the gradient is, what the roughness coefficient might be. Looking at that hill slope over there might be asking, what is the groundwater contribution from that hill slope? Seeing that snow in the back, what are the stem-up processes that control this? Similarly, a biogeochemist might look at this and say, oh, I see a stand of conifers up there. Might have different DOC quality than the deciduous trees I see in the foreground here. Are there redox zones around here? What's the extent of this hyporheic exchange in this kind of gravel stream? What's the mineralogy of the cobbles and the overall superficial geology? What's the chemistry of the water? A geomorphologist looks at the same picture and sees something yet again, noticing we have a glaciated valley. There's a certain size of the parafluvial zone, looking at the thaw wave of the valley versus what the stream, how the stream moves around that, how well sorted are the gravels, etc. And you'll see I'm not a geomorphologist as I go further and further into these different areas. An aquatic ecologist might look at the stream and see yet another set of properties, wondering about how oligotrophic the stream is. What's the carbon source? Is it a lochtinous or a autochthonous carbon source? What's that backwater habitat and the role of that as a refugia, for example? What's the substrate size and stability of the substrate? What's the benthic community look like? So the point is, for each scientist, for each environmental scientist, we bring a body of theory to this picture, and we bring our process knowledge. We have perceptions of this place, and we bring our intuition together. And we put this together then to reduce the physical world to a set of, or to one or more conceptual frameworks. Now, in addition, we add to this measurements. And so some of these are quite standard measurements, like water quality and quantity, or meteorological measurements. We might have other measurements like remote sensing, which are more continuous fields, or survey information like vegetation surveys or digital elevation models. Or we may have something that is, more exotic, such as DNA sequences of some microbial community that is being studied. But if these data are geographically referenced, they come together and form, if you will, a data representation of that same place. Now, of course, there's an interaction between that conceptual framework and that data representation, because our conceptual framework helps us say where do we want data and what do we think, what do we perceive as similar, what is different. But also our ability to measure things can change our conceptual framework. So there's a feedback then between the data we're able to measure and the conceptual framework that we are working with, as I said, which is a function of our training and our understanding of theory. Now finally, we add mathematical formulae and various solution techniques to these data and conceptual frameworks, and we form various model representations. And of course, the data feeds back into the model through a validation step. Now, these three aspects, the conceptual frameworks, the data representation, the model representations, all told are what I'm going to call the digital. An important point to me in this is that notice that I've said that we have, plural conceptual frameworks and model representations, but a single data representation. And I think that one of the outcomes of our efforts in the HIS project has been to recognize or to believe that perhaps we can have a single data representation which will support multiple conceptual frameworks and multiple model representations. So let me explain a little bit more about what I mean by this data representation. So it is in essence the database, but there are properties of this that we want to emphasize. So first, it's very important that our data are placed within a four-dimensional framework of time and space. And so this means that we want to develop the ability of being able to move as easily, if you will, around space as we do right now in a time series across time. This requires still a fair amount of work. There's been a lot of efforts there towards this, and it's certainly about doing four-dimensional data representations. But it's not to say it's ready today. Secondly, this data representation should be continental in scope. As I'll explain in a minute, that's another outcome of our efforts is seeing that we can, in fact, begin to federate data sources to come up with a comprehensive continental picture. This data representation has to be multi-scale and multi-resolution. In other words, the same data representation should be able to hold the continental scale data, for example, at a 1 to 1 million scale, but also be able to hold your project's data with that fine scale, 1 meter DEM, also should be supported by this data representation. So the picture I have in my head is like when you're using Google Earth and you fly over different parts of the world, and some areas have greater resolution. And in some sense, that's what I see the observatories to be, is that you'll go from having the standard 30-meter DEM coverage, which is present for the entire continent, but then when you promote a high-resolution DEM, that will pop up on the screen that is available. Next, this data representation should incorporate not just point data, our typical time series data, but also has to include GIS coverages and dynamic fields, such as, in this case, that picture represents the North American reanalysis of climate. So this is probably precipitation or evaporation for a certain point in time, which is in this continuous gridded picture. NextRad data would be another example of a dynamic field. So the digital continent then holds out the possibility of integrating both monitoring and research data to yield a single body of information for the country. In this sense then, observatories contribute intensive information to this body, but it contributes the same body of information. The observatories benefit from this approach because they're placed within the context of climate and geology and soils that are not assumed to be representative in any particular area. They are present at a particular place. And like every place, there's some aspects of that place which are unique. And finally, I think that as we have explored this concept more, I think our notion of what an observatory is has broadened to be not just watersheds, but they may be aquifers, river reaches, or any region that's part of this continent. In that way that we may be studying very large-scale problems, let's say, for example, hypoxia in the Gulf of Mexico. But to understand that kind of problem, you need to understand not just what's happening in a particular agricultural basin, for example, maybe where a standard watershed approach is appropriate, but also you need to understand what's happening in the main stem of a large river or in a or a reservoir in a large river that might have multi-year residence time. All of those things could be valid observatories in this concept. So, and this has emerged really with the work of the HIS group, where we start with, and this is what they have been working on, is taking and federating multiple sources of data, such as shown here. So we have the Ameriflux towers that's supported by NASA and DOE. We have the NOAA automated surface observing system at the airports around the country for climate data. We have the USGS endless system of surface water and groundwater on water quality sites. And we have the NOAA Climate Reference Data Network, which is the high resolution and high quality climate data at areas which are considered background stations for looking at climate change. And with this federation scheme, these come together in that we can actually have a common portal and look at a single map with all of these data available together. That's what sort of gave rise to this notion of a digital continent that this seems to be within reach now. Now, with the digital continent, we can talk, I think, a little bit more specifically about the inference space from our observatory. In some sense, one general objective of the observatories is to be able to extend place. In other words, to take an intensively studied place and transfer the results to a less intensively studied places. Well, by having a digital continent, that will enable identification of whatever similar means by your hypothesis. And indeed, there'll be some data collected by any number of agencies about that spot. Perhaps not sufficient data, but enough data maybe to test an inference. And so we can start looking at observatories within this context that will enable an inference about similar regions. So, presumably if you're studying the Potomac River, you should be able to infer more about the Delaware River than about the Rio Grande, because we would believe there are more similarities between these two adjacent basins than would be between something which is a very humid basin to an arid basin. So what I would like to contend, and I'd be happy to have people, what I'd like to have people to think about and maybe disagree with, is that I'm holding my premise is that the digital observatories, in fact, are the foundation for environmental observatories and such as CZOs. And I think that these form a basis for collaboration of mission and science agencies in a way that we've never had before. That the digital observatories can contain both the monitoring and research data. That the digital observatories, by supporting multiple conceptual frameworks and multiple models, can support hypothesis tests, decision support systems, and management models. For us as environmental scientists, I think it's very important as well, because I think that having these digital observatories and in the context of having these multiple conceptualizations and multiple models supported by the same data, that scientists can access multiple conceptualizations to improve understanding and communication. And furthermore, everyone can benefit from the context provided by all the other data. So our sense is that incentives, well, first, that incentives must exist for people and agencies to want to contribute to the digital observatory and the digital continent. And our experience to date is, in fact, they do. The USGS has been very supportive of these efforts. In fact, is moving to adopt quasi-web standards for the NWIS database. The National Climate Data Center is doing the same for a set of their databases, and the EPA STORET people are also very interested, and we're actively talking with them. So the agencies have been very intrigued by this, because people can begin to see the benefits arising from this kind of collaboration, and the cost of doing it is much reduced by using modern technologies of web services. So I wanted to also give an example here of where a lot of the data being collected by agencies like USGS and EPA are of great interest to academic researchers. So, for example, this map just shows standard USGS water resource regions and their hydrologic unit codes at the 8-digit level, and it highlights this one area up here in Oregon. There is a coverage that's been developed called NHD Plus, National Hydrologic Data Set, Hydrographic Data Set Plus. This is for one particular region in coastal Oregon. This data set is a national hydrography data set, which has not just all of the streams, and streams are all in a network context, what's upstream and downstream of each other. All for each of these streams, a catchment has been clipped out for each of the streams. Now, this is done at a resolution of 1 to 100,000 hydrography. The average reach length is 2 kilometers. There are 2.3 million reaches for the continental U.S., and the average area of these catchments are 3 square kilometers. This is definitely coming now down to being of great interest to researchers, because this is becoming down to a scale and resolution that's relevant to even quite small-scale studies. Now, each of these reaches have already been attributed with their slope, their elevation, an estimate of mean annual flow and the corresponding velocity, their drainage area, and a percent of the upstream drainage area in different land uses, and the stream water. There's quite a lot of information there. We're working with USGS and EPA to try to figure out how to serve this data and to make this more accessible to the research community. But this provides a tremendous kind of framework for placing our research studies into. Now, what's available now and what's just a figment of my imagination? We're shooting for a 1 November release of HIS 1.0, so very, very soon, in a few weeks. And what we've really focused on to date in HIS are point time series. And that's both a way of trying to discover the data and from mission agencies and from federal data providers, as well as publishing data from academic researchers. The agencies we've been working most closely with have been the USGS for the NWIS system, the National Climate Data Center, and the EPA STORAD system. We're also talking with the LTER TRENDS programs and long-term ecological research sites. They are also compiling data for a study called TRENDS, and we think it should be a fairly simple matter actually to bring that data and federate that as well. Right now, we're looking at trying to develop static federation to the observatory testbed. So the NSF either has awarded or is in the process of awarding a total of 11 studies under the WATERS program. These are short-term, 2-year studies for observatory testbeds, and these will form an interesting set of sites for us to try to see how to federate quite disparate sites with different kinds of data systems together into this system. So the overall HIS architecture is that we have a server and an analyst side. So on the server side, we have the national scale server is hosted by the San Diego Supercomputing Center, which provides a map interface, which I'll show you in a moment, the observations catalog and web services to the national data sources, such as USGS. We, in addition, would have the Workgroup server, which is going to be at the level of the River Authority or a university or a research center, to host the regional data. So it would be exactly the same software, but the data would be customized and allows greater flexibility to allow the data federation to occur at this level. So, for example, state data could be coming in and other local and regional data sources, as well as the individual investigator data. Now, the server is then used by from the other way around, by the person, by the scientist wanting to access the data. There will be application templates and what are called Hydrologics for direct ingestion of data into analysis environments. The point here is that although there may be quite a lot of differences in how data are formatted among all these providers, that the web services will provide the interface to allow the user using a common interface to discover and then download the data directly into their analysis environment that would handle all these formatting issues. So the HIS server supports data discovery, delivery, and publication. So data discovery is a map-based interface at this point, and it's going to basically show the location of different kinds of data, and it will provide access to the metadata explaining what data are collected where. Data delivery is using web services to retrieve from the local database or from the remote data sources. And then we've also then developed, this is a representation of the data schema for point data, whereas if you choose to place your data within this data schema, it will come already wrapped for the appropriate web services to publish the data automatically using the observations data model. In addition, if you want to do the programming, you can take any arbitrary database and wrap it with these kinds of web services. So we have then these two different levels of servers, the National HIS and the Workgroup HIS. From the National HIS, what you'll see is that there will be a polygon on it indicating that there's a region of more intensive data available, indicated here. When you click that, when the user would click that, they would then go to the Workgroup HIS. And right now, we're just doing this as a static registration process. Eventually, the idea would be to have this thing dynamically linked where people don't have to get involved to actually register the data, that you can just announce the national system, and then there'll be some authentication scheme to handle this. But right now, it's a manual step. And again, this workgroup level has the local observations catalog for the coverage of the national data sources in its regions. And then these local catalogs can be partitioned in from the national observations data catalog. So the overall scheme here is, in the way the computer scientists talk about this, is an extract, transform, and load scheme of where the concept is, or the vision is that the quasi-web services would be able to extract from a variety of data sources, both the agency data providers as well as academic research data, and then transform the data into the appropriate form and deliver it into the analysis environment of your choice, whether it's Excel, ArcGIS, MATLAB, etc., as you can see. And so these various, the arrows that are indicated by orange, these are all data sources and data receptacles, if you will, that have been prototyped to some extent. Some are more robust than others. But these, in theory, at least in concept, these kinds of transformation services will work. So here's an example out of Excel. What you would have is in the Hydrologic, which is essentially a macro that would be in your Excel spreadsheet. You put the parameters into the macro, and you click on a button. That actually will then go hit the web services using these various web methods to the Hydrologic, which parses this request and recognizes that it has to go out to the web to get it. It will then go to, I believe it goes to San Diego to format the query. The query then goes to the USGS database to get the data. The data are then returned in XML form. The XML gets translated back into Visual Basic Objects. The Visual Basic Object is then imported back into Excel. What you as a user see is that you click this and you end up with a graph. In fact, there's all sorts of things happening in the background. The point I wanted to get across here is that this is not just using a web page to get data. It's far more sophisticated than that, that you're able to put this within your analysis environment of choice, and that all the sort of formatting and date stuff and all that crap that takes so much time to deal with is handled in the background. That's the concept. And where we are with this is that the extensive work that's been done with the HIS group to date has been with point data, the hydrologic observation data, so your point time series data. These other data types remain to be done, and those are the geospatial data, such as GIS coverages, remote sensing data, which is in this EOS HDF format, and weather and climate data in NetCDF. Each of these areas have been explored to some extent, but we're some distance away from having operational services to manage those data types. There are many more complexities involved. So for Digital Observer remains on the data representation side is to get develop these integrated four-dimensional database. Again, not a minor developmental issue, although there are a lot of ideas about how that should be done. To add things like GIS coverages, which are relatively easy to serve, and dynamic fields, which is far more complicated to serve. On the conceptual framework and modeling, this is really so much more of a developmental effort of asking the question, well, can a single data representation actually fulfill a diverse set of science needs? Both the WATERS testbed sites and the proposed CZOs could actually be an important test of whether this concept can work. And then how do we do the feedback so that we have that digital observatory to do the data assimilation techniques to guide sensor deployment and operation and collection of additional data. And for the extensions to HIS that have been explored, one is integration of weather data. There's been a small pilot project headed up this summer by on a small prototype on the Ohio River Basin. And the outcome of that has been looking at trying to move from the typical gridded atmospheric science products to watershed-based delivery of data. And this would also be using the NHD plus catchment scale. And so that's been explored and seems to be feasible to do that. On the hydrogeology side, when one sees these pictures of the continent emerging, an obvious need comes out of trying to construct the stratigraphy for the continent. Again, that's a lofty goal. How can we get there? What can we do? Recognizing a lot of this information is held at the state level. So how can we use the Federation? How can we build upon some work on stratigraphy that's been done by the GEON project that's been trying to do the mediation among all the different nomenclatures for stratigraphy? How do we build in a geologic framework and make that more accessible to environmental scientists as they're developing observatories? How do we build in the geomorphic and geologic history, something which is much more fuzzy than a straight, clear representation of this point in space represents something. The geomorphic information is not so precise as that. And then how do we incorporate the human dimension? Transportation, structures, permit data, toxic release inventory, etc. Floodplain information, for example, there are private companies that do that process thousands of real estate transactions a day on determining whether some parcel is inside or outside of a floodplain. They have products that are obviously very commercially valuable, but if we could get access to maybe some outdated products from them, from their point of view, which doesn't have commercial value, but would still have research value for us. In addition, FEMA is doing extensive LiDAR mapping. What we're getting to here is that bringing this data together, of course, is a huge job, but the federation if people can adhere to certain standards, so that this becomes more possible now than we ever thought it could be in the past. And furthermore, we need to then move, which we've seen all along, there's just been the conterminous U.S., we need to move and plan to move to explicit development for support for Alaska, Hawaii, and Puerto Rico beyond the conterminous U.S. That's clearly necessary here. So, what about HIS and CZOs? Well, CZOs can deploy Workgroup HIS, and we would hope this will be released very shortly, within the next month, certainly by next June or whatever, when the CZOs are funded. We think we should be ready with a more mature version of the software. As you're thinking about proposals, what we would suggest you need is a dedicated server, order of $5,000 for that. You would need software of ARC server, SQL server. This is potentially free. Microsoft Esri has been supporting us in providing both services and free software to CUAHSI. They probably, in many of your universities, already have some kind of site license already for ARC. On the SQL server side, Microsoft has expressed interest in supporting this effort and may be able to provide free software on the SQL server side. HIS should be providing a data loader for the point data. This is the observations data model should be provided by HIS. But we would suggest that you certainly need probably a full-time information manager for each of the CZOs. This would be comparable to what the LTERs have now. HIS can provide to you data catalogs for point time series and coverages such as that HD+, and registration in a national catalog to help you publish your data. These are the kinds of services which we think we can provide, and which should be in pretty good shape to provide by next summer. Now, CZOs and CUAHSI. CZOs are a very high priority for support from CUAHSI. For example, under our Hydrologic Measurement Facility pilot project, we have a geophysics activity going on there headed by Rosemary Knight. Rosemary is actively seeking watershed partners for evaluating how to deploy geophysics services. The first two pilot studies happened this past summer, one at the H.J. Andrews Experimental Forest in Oregon, an LTER site in U.S. Forest Service Research Watershed, and another at an ARS site at Reynolds Creek, Idaho. Also, the CZOs form a beta test group, just like the waters testbed sites are, for HIS products, and help set priorities for development. What do we do next, and how do we determine what to do? And for community access, obviously we're here to help with the data publication, such as through this HIS system, but also I think we want to talk about supporting the development of basic user guides and education and outreach activities to the broader community. So finally, beyond CZOs, the operation and maintenance for environmental observatories is emerging as a major concern for NSF. I think that experience is gained through the EarthScope project in the seismology community, as well as when NEON is coming into greater focus about what it will entail and what it will require. What we're hearing in the Geosciences Directorate is a great deal of concern about operations and maintenance. And I think the way forward on this is to really seek the active engagement from the science and regulatory agencies like USGSs, like the NRCSs, other agencies that are out in the field now to develop collaborative observatories. The academic research can provide new technology and basic research, and importantly, students. Innovation agencies can provide operational support, infrastructure, and of course pursue their own research agenda, often an applied research agenda. And we want to use the CZO experience as a way of tailoring and designing effective engagement of mission agencies. So as you are developing your proposals, we'd be very interested in working with you and helping to see what your experience is with engaging local and federal state agencies in the CZO design, and communicating that message of how this can work up the chain, because this is going to be a very important factor as NSF evaluates the viability and utility of these kinds of environmental observatories. So I would, with that, which is basically a half-hour talk, I would like to stop and basically open it up for questions. I hope I've given you some ideas to think about here, and have given you some opportunities to consider how you might want to construct the CZOs and how the CZOs can fit into a broader context. So with that, Tequila, if you want to request questions from the audience, and people can begin to ask questions or type type them in to your chat box. Hello?
Ladies and gentlemen, if you wish to ask a question, please press star 1. If your question has been answered or you wish to withdraw your question, press star 2. Questions will be taken in the order received. Please stand by while we compile a list. As a reminder, press star 1 to ask a question.
Well, I hope I didn't leave everybody speechless. Okay, from Henry Lynn we have, has HIS considered or planned to incorporate NRCS soils databases? Henry, I think the best answer to that is I know that that Doug Miller at Penn State, who's working with the CZEN infrastructure, has been looking at these databases, and Doug has been talking with David Mayman about how to do this in a compatible way. So the answer basically is yes, indirectly. We certainly want to do that, and I think that's part of the power of the technology we're talking about, is that federating these different sources become relatively straightforward to do. Do you have any questions in the queue?
Yeah. I'm still showing no questions in the queue.
Okay, we'll give you a few more minutes if you have anything to ask. I would be very happy to get any feedback on these concepts and what you think might be useful and not useful about them. So certainly feel free to contact me with any issues. Let's see, we have a question: how far is HIS in serving spatial data sets? David Mayman would be the best person to answer this, but as I understand it, there is a GIS USA server put together. The issues had to do with how one clips out portions of these very large coverages to serve them. I know that there are some technologies that are out there, some that have been worked out at San Diego Supercomputing Center for how to provide that. I'm not positive how far they are in actually providing that service to be able to do clipping of databases on the fly and delivering to you only that portion of a database that you need. It's relatively trivial to just serve a given coverage, but to be able to subset the coverage is a bigger question. Let me see if I can keep up with all these. Any plans to incorporate from Rutgers University? There is a plan to work on what are called hydro volumes, and Esri has been extending their support for hydrogeologic representation. As I understand, the RASA products were all in the pre-digital age, and I believe those are all paper products. If I'm wrong, please correct me. But this is where I think we would like to explore and maybe put together, if there are groups that are interested in, some kind of pilot study to show how we could move things like the RASA studies into digital coverages. Is information on the number of CZO letters of intent available? As I understand it, this is still a confidential number. Let's say that what I've heard is that there have been many submitted. Many letters of intent were submitted. How about the synergy between coastal environment observatories and HIS? I think we have not explored that as far as we might. There is one of the test beds, or two of the test beds are in coastal environments, maybe three, let me say that. There's one at Corpus Christi Bay, one in the Chesapeake Bay, and there is one down in Albemarle Sound. So we are beginning we are beginning through those groups to explore how the coastal observatories will contribute. But notice that there is a distinction between the OOI, the ocean sciences coastal observatories, which tend to be continental shelf, that's by what they mean by coastal, versus really embayments. So I would say what we have gone out is as far as into the embayments, but not out to the continental shelf yet. Let me see. How do HIS and CZEN cyberstructure different, how much overlap is there, from Suzanne Anderson. The answer is that there's quite a lot of overlap, and we are working with Doug Miller for the CZEN cyber infrastructure to make sure that it is compatible. And at first blush, at least in our initial consultations, it appears like there shouldn't be any particular issues. It should be relatively easy to integrate. And yes, Rutgers confirmed that yes, RASA are paper maps. And so I think this is yeah, with the map structure, we have to figure out how to get this into an effective digital representation. And as I understand it, there's one implementation of these 3D hydro volumes has been created, but they're talking about developing additional tools for this data structure. So what I would encourage is the hydrogeology groups that are interested in this, if they would please contact me. I'd be very interested in pulling a group together and maybe getting some kind of proposal put into NSF about exploring how to bring in stratigraphy and the hydrogeologic structure into a digital framework. That would be of great interest to many of us. Any questions in the queue?
Your first question comes from the line of Matt Larson. Please proceed, sir.
Thanks. Hi, Rick. Can you hear me?
Yep, I can hear you, Matt. Go ahead.
Great. You know, there's some pretty exciting stuff you've put up there for us to look at, and I would assume this goes without saying, but I would just encourage anyone who's developing letters of intent and assembling groups to develop proposals that for the mission agencies, you'd want to involve us as early as possible in the process. The big issue, of course, is always how do you fund the salaries for these folks. And so if there's a good alignment in terms of the goals, the capabilities between the academic and the federal side, and trying to work it with some kind of a good co-location of where these people are, we're more likely to be successful. I know of at least a few proposals where that's already in process, but I don't, as you mentioned, it's a confidential number. I don't know of that many offhand where other people may be launching into this effort, and whether or not they're involving their counterparts in, you know, Forest Service or NRCS or GS.
Right, exactly. I think it's a really big issue, and I've been in touch with Matt earlier, and this is something which we need to work from both sides, from both the top down as well as the bottom up. But for those of you out there, yes, I think it's critical that you engage your various mission agency sources, both federal and state level, because I just think that these efforts will benefit so much from the experience and the technical abilities of those mission agencies that have operated these field facilities for so long. So thanks, Matt. Glad you could join us today.
As a reminder, press *1 to ask a question.
Okay, well, if we don't have any other questions, I think people have had time, then thank you, everybody, for coming. I hope you found this informative. And as always, we're always looking for feedback. Feel free to send me a note, an email, or give me a call about if you have any comments or concerns or questions. So I guess we will wrap it up there if there are no questions, and thank you very much for attending. Goodbye, everybody.
Thank you for your